Hi, my name is Camille Chudek, and this is my Fall 2020 ISM project focusing on a feasible waste gasification method specifically for the production of syngas in developing countries. This is just a disclaimer saying that I did not provide all of the information on my own, and some of them were from outside sources. For my project, I focused on engineering research, and my mentor was Roy Anderson, the robotics teacher at Clearbrook High School. This slide shares information about the ISM course, but for my project, I focused on waste gasification. Because of growing issues such as consumerism, landfills have become an immense problem because of the pollution they create through emissions and runoffs. However, gasification is a process that allows carbon-based materials to be turned into energy and useful products through the use of high temperatures and oxygen-starved environments. With that said, waste gasification can prove to be a useful solution to mitigate the effects of landfills and also establish an alternative electricity source for developing areas. Through my research, I found that waste is mainly disposed one of two ways: incineration and landfills. However, both of these options have a variety of negative environmental impacts. With that said, gasification would be a much better option. However, gasification is mainly only practiced on coal and biomass, and its most efficient methods are expensive and use inaccessible technologies, such as plasma arc gasification. I also found that researchers are trying to reduce the environmental impact of gasification even further by using nanotechnology. However, once again, this is inaccessible to many developing areas. That said, for my project, I wanted to design a waste gasification system that could be accessible to developing areas while also have no negative environmental impacts. For designing the product, I used the engineering design process, and included on the slide are some of my sketches. Along with this, I wanted there to be no harmful emissions, and so I went with the solar method of creating heat rather than using plasma technologies or using the burning of a material. On this slide are two parabolic mirrors. On the left is the first one I created for this project, and on the right is the last one. And starting on the right, we have the feed canister. And for that, I solely use leaves, and this is because I wanted to just focus on the function of the system rather than also worry about another component, which would be the heterogeneous mixture of the feed. So I just kept it consistent by using dried leaves. Next, I used the parabolic mirror as a heat source, and you can see it on the feed canister there. And then for filters, I had two, and the first one was a water-based one. It's just water, and it's also known as a steam condenser because it condenses the liquids in the gas, and then it also removes unwanted materials such as tar, ash, and smoke particles. And then after that, I also had another filter that had filtering paper and wood shavings. And then in between was a bypass valve. This was in between both of the filters in case of an emergency. And then lastly was the collection method. So for this, I wanted to use volume since it's a gas, and I used the water displacement method as shown here. So these are the problems I encountered when executing my project. The first one and the main one was the heat source. Although the parabolic mirror had a focal point, it did not generate enough heat to heat the biomass and create a gas. With that said, I turned to alternate conventional methods such as a stove and also a propane torch. I used both of these for extended amounts of time, over 30 minutes, and I also used a combination of both of them when each of them individually didn't work. And with that said, I was still not able to obtain any gas, even though I was hitting the correct temperatures. So after opening up the canister, I learned that it actually wasn't the heat sources that were creating the issue. It was the moisture that was within the dry leaves that I used. There was quite a bit of moisture, so because of that, it couldn't burn and create a gas. So that was my experiment, but more artifacts can be found on my website that include more details such as my procedure and materials, as well as other notes I took along the way. Overall, even though I wasn't successful in creating a gas, I still made this system, and the issue didn't lie within the system, it lied within another component. However, now I have the knowledge to look into pretreatments for drying feedstocks to move further, but overall I would say this was a success to get to the level that I did. Okay, thank you teachers, evaluators, and mentors for watching my presentation. There's me and the butte itself. Here are some predicted questions. Why did I resort to commercial methods instead of trying to stick with solar and modifying solar? I honestly had doubts with solar because the temperature was 60 degrees and it would have to generate a high amount of heat. So I went with commercial just to see if the system would work by itself with a different heat source. How can I apply these findings to the real world? Well, the system itself can still be used. It would just have to have a pretreatment applied to it to dry the biomass or the feedstock first. And then would this be realistic to scale the system up to support communities? It would be realistic as long as the community has an abundant amount of waste to support their feed, and so that it's sufficient. And these are my works cited.